Because it's going to solve Okay, good morning. Let's take a seat. In the previous lecture, we were discussing about different criteria to classify the engine. And the first criteria we were discussing is relative to how combustion is started. So it can be started through an external spark, so an external energy discharge, or we can have self-ignition related to the compression. And we specify also that there are some differences in the fuel, in how the combustion is developing, in how the load is controlled, and so on. Now, we can go to a second possible classification, and this is related to the cycle duration or working cycle. So we can discuss about two-stroke cycle or four-stroke cycle. So this is related in reciprocated engine to the number of revolutions necessary to complete one cycle. So in this one, we have, one revolution that is corresponding to two strokes. So the piston is going up and down. One revolution will be corresponding to one cycle. So we need one revolution to performance. In the four-stroke engine, we will have two revolutions that is corresponding to four strokes. So here we can say piston up and down. And here we can say piston up and down two times. Two revolution is corresponding to one cycle. We will use also in calculations a letter that is called, we will talk about a letter we will refer to M equal to 1, so number of revolutions per cycle, M equal to 2, number of revolutions per cycle. Yeah. Let's start with the four-stroke cycle. So the piston is going up and down, we were saying two times, so from TDC to BDC, down or up. And in this cycle, we will have several phases. How many phases? Generally, you find in technical books, four-stroke, four phases, but this is not correct from a, let me say, from a phenological point of view. How many phases? It sometimes also depends on the book that you are reading. Let's talk about scientific book and not technical magazines. I will prefer to consider 6 phases, but sometimes you can also find 5, and I will see. So we will discuss about 6 phases in 4 strokes. We will find that for some of the phases, we have the same name of the stroke. So we will call with the same name. But strokes means always is something geometrical. So it means from TDC to BDC or vice versa. So stroke means that we have a movement of the piston of a distance that is called the stroke. The phase is relating to different phenomena that are occurring inside of the engine. So, and we will distinguish between among different phases. Here the phases are indicated with Roman numbers. Okay. In 4-stroke engines, let me say around 2 strokes, and this is what is distinguishing between 4-stroke and 2-stroke, more or less 2 strokes are dedicated to the gas exchange process. I remind you that in combustion, we're starting from air and fuel that are also called reactants, or is the mixture, or is the charge. We have combustion, and we get, let me say, we can call them exhaust gases, exhaust gas, or anyway, these are the products. So reactant and products is more a generical chemical description. So what we have is that there is a change in chemical composition. So the cycle that we are going to describe is an open cycle because we have to replace the exhaust gas with fresh charge. And practically 2 strokes are dedicated to this process. So we can say that change exhaust gas after combustion with fresh charge. And as I was saying, 2 strokes, roughly 2 strokes are dedicated to this. And here at the bottom, we have a diagram in which we plot the pressure that we have inside the cylinder with respect to the volume. Maybe here the resolution is not that good. Anyway, we can also try to replot it. So if this is the pressure, this is the volume. Here we have TDC, and this will be the clearance volume. We can also indicate here, sorry. Anyway, because clearance volume will be related to this distance. And here we have the maximum volume corresponding to BDC. So clearance volume is this part or is corresponding to this side. Here we have the ambient pressure. So we will have different phases, in particular, the phases that is related to the exchange gas process can be done, let me say more or less, we can have a diagram that is done in this way in what you see on the other part. So we have something like this. So maybe here the resolution is not that clear. There is something like this, more or less. We can have here a passage going down. It depends on what you are. Passage like this. Let's have a look at the phases, and after we can rediscuss about this process of gas exchange. The first phase that we are considering is intake. And here we can consider also the phases describing the position of some valves that are used to let the fresh charge come in or go out. So here we have some valves, and we have at least one valve of this kind for each engine. We have a valve that will be called intake valve, and there is at least one valve that will be called exhaust valve. So I and D stands for intake and exhaust. During the intake phase, the intake valve is open. The exhaust valve is, as you can see here, is closed, but actually you can have a moment in which the exhaust valve is partly open. We will describe maybe better afterwards. So let me say, if we want to be more precise, mostly closed. So this is the phase in which fresh charge is entering the cylinder. The duration of the intake phase is longer than the corresponding stroke. So we have the intake stroke is when the piston is going from top dead center to bottom dead center. But the actual phenomenological phase can last longer. So intake phase is longer than the corresponding stroke. The stroke is corresponding to half revolution. So if we is 180-degree rotation of the crank, so generally we write this symbol, degree of crank angle. It's maybe easier to explain or to show in degrees with respect to radians. But you can also use radians, that is the unit for the international system. Okay. The piston is going down. The charge is entering. The charge can be either air and fuel or simply air, according to the engine that we are considering. This phase is what we have from the point 6i to 1. And also on this diagram, you can check that 6i is reported here. And 1, it depends on, but can be maybe roughly here. So you can check that this diagram will be considered in this direction. So here, you can check that the intake stroke will be from TDC to BDC, while the phase will be longer because it starts before reaching the TDC. You reach the TDC, you go down to BDC, and the piston is going up. So more or less, we consider the point 1. These numbers are considering the separation of different phases. So the phase is longer than the corresponding stroke. So intake phase 6i1, corresponding stroke is TDC, BDC. So we are considering the entering of the air. One stroke is practically, or even more, is dedicated to this process. More than one stroke is dedicated to this process. After this phase, we have the phase of compression. So we can also, I can add maybe compression. Both valves are closed. Let me use the intake valve and exhaust valve. Closed, closed. The phase is also a corresponding stroke. And here we can say that compression phase that is going from 1 to 2 is shorter than the corresponding stroke. So we have a phase that will be called compression, a stroke that will be called compression. The difference is in crank angle degrees is present, and the phase is shorter. The corresponding stroke is from BDC to TDC. Point 2 is occurring before reaching the TDC. So I can also complete the diagram here. More or less, we will have something like this. Here we have point that will be called 2. So from 1 to 2 is shorter than the corresponding stroke. Okay. Let's go to the next phase. Here we have combustion, phase indicated with number 3, and is going from point 2 to 3. Here is quite maybe easy to see the points. During combustion, right here, 2 to 3, both valves are closed. During compression, we had the reduction of the volume, the increase of pressure and temperature. At a certain point, combustion is starting. Combustion will be related to either spark ignition or compression ignition. It depends on the engine that we're considering. So we have a spark that is occurring or a fuel that is injected. Here, there is no practically corresponding stroke. There is not a combustion stroke. Because combustion is occurring around the top dead center. So combustion is around TDC and can last for a certain crank angle degrees, hopefully not too long. So let me say desirable duration, not too long to have a proper combustion, just order of magnitude minus than 50. Okay. And is occurring here around top dead center. So there is no corresponding stroke. During combustion, we have a, as you can see, high increase of pressure and temperature in the combustion chamber. Why do we want a high pressure? To use the next phase, that is expansion. During the expansion, that is going from 3 to 4, both valves are again closed. And this is why we are building our engine. So we have a corresponding stroke. So, and we can say that expansion phase is shorter than the corresponding stroke. Because you can check that 3 is after top dead center and 4 is before top dead center. The stroke is always from TDC or BDC or vice versa. The phase here is going from 3 to 4. This stroke is also called power stroke. So we can talk about expansion stroke or power stroke. And this is, I would say, the motivation why we are building our engine, because we want to obtain a power generation inside the cylinder in order to move the vehicle. For instance, move the vehicle or obtain some power for something else, so electrical power generation. But for our application, we are talking about moving the vehicle. This is, as I was saying, the fourth phase. Let's see the other phases. Here we can have a distinction in 5 books, in some books, and this is why you can find 5 or 6 phases. Because in some books, they are saying there is an exhaust phase that is going from BDC to TDC. In these lectures, I used to split this exhaust phase in 2 different ones. So last stroke is missing, so this we will have the 4th stroke. That is going from BDC to TDC. We are considering the 5th and the 6th phase. We are talking about the blowdown part of exhaust. In this phase, the intake valve is closed, while the exhaust valve is open. When you open the exhaust valve, the pressure in the cylinder is still high, because 0.4 is this one. When you open, consider the opening of the valve. This is going from 4 to 5, 4 to 5. The pressure is, as I was saying, is high. 0.5 can be here, 4, and let me say 5 here. So what's the point that here was corresponding more or less was here, sorry, here, okay? No, sorry, more or less here or here, depends on, anyway, on this line. What is occurring here? Due to the differential pressure, I have that exhaust gases are going out from the cylinder. Differential pressure between what you have in the combustion chamber and what you have outside. So pressure in the cylinder during the exhaust is higher with respect to the ambient pressure. So pressure in the cylinder during this process. We can split between blow down and displacement, and the difference related to displacement is occurring later. The blow down is likely occurring before reaching bottom dead center. So 4 is before reaching BDC. 5 will be after BDC. And displacement is occurring between 0.5 and 6E. So we can call the displacement part of exhaust. Intake valve is closed mostly, while exhaust valve is open. Mostly because here we are going from 5 to 6E. So here we have 6I and 6E. And we're moving in this way. When we reach 6I, intake valve starts opening. So during this part, actually, both valves are open. Okay, so this is why I wrote most. Which is the difference between blow down and displacement? Here, the exhaust gas is not going out due to differential pressure, but the piston is pushing out the exhaust gas. We have also to consider that on the power stroke, power generation that is used to move the vehicle, the gas is doing work on the piston. While in this phase, we have the opposite. The gas is requiring work to the piston to be moved, or the piston is doing work on the gas. So this is what we actually don't desire, because we would like to receive work from the piston and not to provide work to the gas. So let me say this is a detrimental phase on what we are considering. After this, the cycle is repeated. So the difference that you can find in some books, for instance, the book that I generally consider as a reference, the book from Haywood, is considering 5 phases because he's considering just probably someone from home has opened the microphone, so can you switch the microphone from home? Switch off the microphone. Okay, so someone, so Haywood is considering just what phase exhaust. He's not distinguishing between what is related to a differential pressure, so no work given by the piston, from what is instead related to the movement of the piston. Here, I prefer to consider different phases. Anyway, what we have is that in a 4-stroke engine, we never can consider simply 4 phases, because combustion is always present and doesn't have a corresponding stroke. But combustion is an important phase, because without combustion, we won't have the increase of pressure and so the power generation. So here we can have kind of summary of the strokes. So 4-stroke operating cycle. So what we have here is the number of the different strokes, but we can consider 6 different phases on the 4 strokes. So here I remind you, you have the strokes. Expansion is also called power, and is, let's say, the motivation why we are building the engine. Here we have again the design of the valves, and in this diagram, but also in the previous one, you can check if the valves are open or closed. So you can check that if the valve is considered up, it means that it's closed. If it's down, it's considered as open. There is a device, you will describe this in the applied lecture, that is providing the opening of the valve. So this means closed. And this means open. Okay, this is the design that we are considering also here. We were saying that roughly 2 strokes are dedicated to gas exchange process. So this is replacement of exhaust gas with fresh charge. So we have to dedicate roughly half of the cycle just to take out exhaust gases and put in fresh charge. This is a valve timing diagram.
Change to this from stroke A to stroke B, or stroke A and B, because it's compression and takeoff.
Sorry, I didn't get your question.
Using the 2 strokes, the change the choice should be from stroke A and B, or A and B, because B is the compression side.
Ah, sorry, it was intake and exhaust, you're right. So it's practically, sorry, this one and this one. You're right. So exhaust and intake, we can consider that they are close, but not from this side, because as you are repeating, they are closed, let me say, on this cycle, because after exhaust, you have again the intake stroke. So we are repeating, this is a cycle. So after exhaust, you are going back to the intake stroke and the cycle is repeated. Thank you. So here we have a valve timing diagram. So we are considering opening and closure of the valves. And we can also consider the strokes. So here we have TDC. When we move from TDC to BDC, we have one stroke or vice versa. So TDC, BDC is a stroke, but also BDC, TDC is a stroke. Here we can also check the length of the strokes with the corresponding length of the phases. So we were discussing, and we can start from intake. So intake is this blue. Intake is occurring, so we are considering the motion in this direction. So we can consider the movement in this direction, and we are starting from here, and we are going to here. So practically, we are considering about 2 revolutions. We can consider that motivation will be provided in next lectures, that intake valve opens before the TDC. So here we have the intake phase. The piston is going from TDC to BDC. So the piston is going from TDC to BDC. But we can also provide a short motivation for this. We would like to have the intake valve that is already open when this phase starts. And as the opening and closure of the valve is not instantaneous, we have to open the intake valve in advance in order to have it already open when the phase starts. So here starts the stroke. We open in advance because we would like to have this, in this position, the valve already open. So we will have the intake phase. Air is entering. Air is still entering, so we close the valve with a little of retard. So we have an advance of the opening and a retard of the closure of the intake valve. This is why the blue half circle actually is more than half. So the phase is longer than the corresponding stroke. So the stroke is just half revolution. You can check that the phase is longer than the stroke. So I will write just for this one, but you can consider for all the other similar discussion. So you can say intake phase longer than corresponding stroke. Is this clear? Afterwards, we close the valve. So here we are practically summarizing the cycle, and we discuss what we have discussed in the different pictures. So here we have compression, this light violet. Compression is from point, we can also add, if you want, the number. So this was 6i. Here we have 1. Here we have 2. So compression is from 1 to 2, and you can check that compression is shorter than the corresponding phase. From 2 to 3, we have combustion, and you can easily understand that combustion doesn't have a corresponding stroke because it's occurring around the top dead center. And I was saying that maybe an optimal duration of this red corresponding to combustion, angle can be, for instance, lower than 50 crank angle degrees. Here, crank angle degrees correspond to the degrees that you can see here. After we have the expansion or power stroke, so we are building the engine for this, and expansion or power stroke is occurring from 3 to 4. You can check that expansion phase is shorter than the corresponding stroke, because the stroke is always TDC, VDC, or vice versa. Here we have together, according to what was described by Haywood, exhaust. So here we have two phases, 5 and 6 together. Blow down and displacement actually are maybe difficult to distinguish. We have 4, maybe 5 can be here. We don't know exactly where it is. And from 5 to 6E, we have the piston. Actually, the piston is moving from 5 to a certain point, but after the piston is going down, so here the piston is not pushing anyway the gases, but the valve is still open, because when we are reaching the top dead center, we would like to have the valve still open. And so we have some advance or retard of closure of the valves, because we would like to have them maybe still open or not closed yet at the corresponding points. You can check that there is a period in which the two valves are open at the same time, intake valve and the exhaust valve, because here we have intake valve opening, and here we have the exhaust valve closure. So there is an angle that is indicated with this red angle, in which two valves are open, and this is called valve overlap period. So both valves are open. For the moment, I'm considering that there is just one intake valve and one exhaust valve. In modern application, it is common to have two valves for intake and two valves for exhaust. We can find different configuration. 1 and 1 can be still adopted for cheaper engines, but is mostly typical to have two and two valves. So here we have described the 6 phases that are corresponding to the 4-stroke engine.
So the intake and the exhaust phases overlap.
For a small amount of time, they are overlapping here. Because at top dead center, during intake, we would like that the valve is already open when the piston is going down. So we have to open in advance. And this is the advance of opening of the intake valve. But when we are pushing out the gases, the piston is going up at the end of the cycle, we would like to have the exhaust valve still open when the piston is going up. And so we have to close the valve in retard. This advance and retard provide an overlap in which the two valves are both open at the same time. And we can also consider that the cycle is not lasting exactly 2 revolutions, but is a bit more, because this point is starting before top dead center, and this point is finishing after top dead center. So you can consider that the cycle is a bit longer than 720, actually, but we will consider 720. So there is also an overlap of one cycle with respect to the following one. So let me say, one cycle is starting a bit before the previous cycle has ended. But generally what we are going to consider is 720, so we cut at these angles. But the corresponding phases is starting a bit early. This will be the reference cycle that we will consider for all the engines that we will discuss in the remaining part of the course. But even if you are not discussing, and we will see why, about two-stroke cycle, at least to have an idea. So we would like to spend at least a description of the two-stroke cycle. Okay. How many phases we will consider on the two-stroke cycle? If the definition of the phases was not unical for the four-stroke, because someone is saying, for instance, 5 phases, even here we can have more difficulties in the phases. Anyway, what I will consider here will be, again, 6 phases in 2 strokes. Yes, one moment. Phases in 2 strokes, that is where we say 1 revolution. Yes, there was a question.
But why you say about cycle, the revolution, around 2 revolution, not more than this?
Yes.
But why do you say same for strokes?
We discussed the 2 strokes. If you have doubts after this, so let me explain for the. Here we have. I can try to distinguish 6 phases, but just 2 strokes. Why? First of all, why do we have 2 strokes? Because here in the 2-stroke engine, we practically don't have the revolution corresponding to the gas exchange process. So we are cutting out the, let me say, I use the 2 strokes relative to gas exchange process. So the strokes relative to intake and exhaust that were used to replace the fresh charge with the exhaust gas are here neglected, are here, if you say cut out, not considered. So we can consider here how the gas exchange process is replaced by the phase that is called scavenging. So gas exchange process with 2 strokes in the 4-stroke engine, here replaced by what we call the scavenging. Sometimes the word scavenging is also used for 4 strokes, but I try not to use in this context and maintain that relative to this one. So when the piston is around bottom dead center, what we will try to have is, so the piston is around top dead center, so we'll be moving a bit before and a bit after bottom dead center. So this is BDC. We have that the fresh charge is entering. So this is fresh charge. Here we have the exhaust gas of previous cycle. And we would like to have the fresh charge entering and pushing out the fresh charge, considering a kind of imaginary surface that is separating the two gases, say. So fresh charge is pushing out exhaust gas. This is the phase of scavenging. It is, I mean, here the identification of the points is even more difficult. Anyway, as we have two-stroke, there is no crossing of lines, so we are going to TDC to BDC, and after from BDC to BDC, so there is just one point. The arrows maybe are not so visible, so scavenging is occurring here. First of all, what we can consider is that as we have just one revolution per cycle, we can simplify the engine and what we have, instead of having valves that are externally commanded, we generally have ports. So we have ports instead of valves. Ports are simply some cuts, some grooves that you have in the lateral part of the cylinder, and these are covered or uncovered by the motion of the piston. Okay, so we have this simplification. Let's consider this scavenging. So we were saying that the piston is around top dead center. We have, in this case, both ports on the intake side and or in the exhaust side are open. So let me say intake port and exhaust port are open. We consider that the fresh charge is entering and is pushing out the exhaust gas. Considering in an ideal world an imaginary surface that is separating the two. This is a real simplification because we are considering two gases. Air or air and fuel is the blue one, and the products of combustion is the orange one. So the two are mixing. So what we actually can have during this process of scavenging, that part of the exhaust gas will remain inside the combustion chamber, and part of the fresh charge will go out to the exhaust without burning. So this is the problem of this kind of engine. So from an ideal point of view, all the fresh charge is pushing out the exhaust gas. But from a real point of view, there is a mixing. So part of the exhaust gas will remain in the cylinder and part of the fresh charge can go out in the exhaust, through the exhaust port. So this is the first phase that we are considering. There is scavenging. And during scavenging, what we have to consider is that the pressure of the fresh charge has to be higher with respect to the exhaust. So in order to push them out. So they are both higher than the ambient pressure because the exhaust, gas, and this is higher than the ambient pressure because combustion is occurring and so the pressure is still high. So what we have to do is to consider that fresh charge must be somehow pressurized. Okay? This must be pressurized with respect to the ambient pressure. Otherwise, I cannot have the gases that are pushing down, because I remind you that gases are normally moving from higher pressure to low pressure. If you have a cylinder that is full of gas, you open the cylinder and the gas is going out. It's never the ambient air that is entering the cylinder, because normal motion is from higher pressure to lower pressure. So also here, if I open the intake port and the pressure there is lower than the exhaust gas, exhaust will enter the intake, and this is what I don't want. This that you can see here is the corresponding to the crankcase scavenge. Is the most simple two-stroke engine that we can find for different applications. So this is the most simple solution to pressurize the intake charge. Simple and, let's say, economical. What we are doing is considering the motion. The piston is going up and down. So consider that in the previous cycle, the piston will be going up. When the piston is going up, here we have volume increase. This element is called crankcase. Crankcase means the case of the different cranks of the engine. So we were describing the crank and the conrod. We have several cranks. They are connected together. They have a closure, and this closure is called crankcase. This environment, so, is what we have below the piston. When the piston is going up, we have that the crankcase volume increases, and so the crankcase pressure decreases. So we can consider here the presence of a valve that is called the reed valve. You can consider this valve as an automatic non-return valve. Made by, for instance, two leaves of steel. You can see them here. You have a kind of valves that are here, connected to something. So when the pressure here is becoming lower than the atmospheric pressure, the air is entering from the external part. So air is opening the two valves, the two leaves, they are open, and the air is entering from the external part. When the piston is going down, the crankcase volume reduces, the crankcase pressure increases, and the pressure of the crankcase, let's call this PC to distinguish, will be higher than the ambient pressure. So here you reduce the volume. This reed valve is not a non-return valve, so the leaf are closed and cannot be opened in the opposite direction. So the air tries to go out to reach the environment, but it cannot reach here the air cannot reach the environment because the non-return valve is in the opposite direction. So non-return valve is just in one direction. So air cannot goes out. Air or mixture. Let me say, let's call charge in general. But is pressurized. Okay. This is the way in which we can pressurize the charge that has to enter the engine during the intake phase, and to have this scavenging process. Okay, so the piston goes up in the previous cycle. When it goes down, yes, the pressurization. At a certain point, when you reach the bottom of the center, this air from the crankcase will reach. Sorry, from the crankcase will reach the intake port. So this is what we were discussing as scavenging. You can find in the two-stroke engine a particular shape of the piston. So piston with a kind of wedge. So anyway, an element. And this is used to improve the scavenging. Improve scavenging, and in particular, reduce what is called short circuit. With the short circuit, taken from electronics, we mean that the fresh charge goes directly to the exhaust instead of staying inside the cylinder. So short circuit, direct communication between intake and exhaust, like it is occurring in electric circuit, in which the circuit is not performing correctly. So this is why you can have a particular shape of the piston that can guide the flow, avoiding this passage. So short circuit would be this one. So before closing the exhaust port, the fuel or the charge, let me say, sorry, is going directly to the exhaust. What we can have on the intake side, we can have and we can distinguish two separate ports. One indicated as intake, and the other one is indicated as charge. The port that is called charge is on the intake side. And this is used to fill more fresh charge when the piston is going up and the exhaust port is already closed. So the piston is going down, we have this scavenging process. When the piston is going up, the exhaust charge, the exhaust port is closed, but maybe I don't have enough charge inside the cylinder. So I would like to continue having fresh charge inside the cylinder in order to deliver more power afterwards. So So we can distinguish this phase here is called intake. So here, fresh charge is still sent to the cylinder, while exhaust port is already closed. To have more charge and power in the cylinder. So I have more charge, I will have more power than the next engine. Okay? These are two, scavenging is completely new. This intake is slightly different with respect to the four-stroke engine. Let's go to other phases. So first, second, third, and fourth phases are really similar to the four-stroke engine. So similar to what was described for four-stroke engine. So what does it? This means that both ports are closed. In the two phases. So all the ports are closed. So the ports are closed, the piston is going up, we are reducing the volume, and so we are increasing the pressure. When we are before reaching the top dead center, we can either ignite the charge or inject the fuel according to spark ignition or compression ignition engine. So there is not much different with respect to what we were describing before. So I think they don't need more explanation. Fifth phase, expansion. Expansion, or again, power stroke. Or let me say, in this case, power phase. Because here we are discussing the phases. The piston is going down, the pressure is pushing down the piston, so gas is doing work on the piston. This is why we are building the engine, to obtain work and power. Once the piston is going down, the piston here is discovering or opening the exhaust port. And so we have the blowdown process. So the pressure that is in the cylinder is higher than the ambient pressure. So pressure in the cylinder during the exhaust. So in the cylinder during exhaust, sometimes I will write G to mean gases. When I talk about PE, I mean the pressure of the gases during the exhaust. Just to do this. This is higher than the ambient pressure, and this is why I have blowdown. So this is as was described in the previous cycle is just due to differential pressure. Or let me say due just to differential pressure between what? Between the gas inside the cylinder and the ambient. Which phase is missing with respect to the four-stroke engine? Displacement. So here, I cannot have the piston pushing out the gas. So displacement is not present. So piston cannot be used to push out exhaust gas. So I cannot use the piston to push out the gas because in this process is not possible. I would like to stress the attention on something that I didn't discuss before. And the attention will be related to the position of the ports. Okay. Let's consider this. And this is why we were describing on the intake one port that is called intake and one port is called charge. Maybe you can have different configuration in the engines, but let's stress the idea on, let's stress something on what we were describing here. When the piston is going down, so consider the passage between expansion and blowdown. So you have grooves or ports that are on both parts. So we are passing from expansion and the piston is going down. The piston is moving the port, is opening the ports. When the piston is going down and you have to consider the exhaust, which port would you like to have taller, the exhaust or the intake? So here you have exhaust port. Here you have the intake port. Now they are roughly designed at the same height. The piston is going down. Which of the two would you like to have taller when the piston goes down and to consider blow down? Exhaust should be taller because if intake is taller, when the piston is going down, the exhaust gas will go to the intake, and we don't want to have this. So when we have expansion and after blow down, let's write already blow down. What we would like to have is that here we can have also, I can also draw this part. I would like to have exhaust port that is taller than the intake. So when the piston is in this position, the piston is going down. This is the height of exhaust port. Let me say exhaust port tip. And here you have the intake port tip. So the piston is going down And here you can have blow down correctly through the exhaust port. Okay, this is what you want. But consider what is occurring after blowdown. You have a scavenging, and after the piston is going up. When the piston is going up, which port? So it's better here to have, or we say exhaust port must be taller than intake port. Clear for everyone? Because when we open the port, the gas is going in that port. And so we would like to have the gas is going outside, so through the exhaust. When the piston is going up, which port I would like to be taller? Which port would you like to have? The intake port. Why?
Those the exhaust and then show the remaining charge
Yes, because if I have the same configuration when the piston is going up, so imagine the same configuration when the piston is going up. So this is exhaust port tip, and this is intake port tip. When the piston is going up, the intake port is already closed. So in this configuration, intake port is already closed, while exhaust port is still open after scavenging. So what does can produce? That
On the charge go out.
that part of the fresh charge can go to the exhaust. And this will be a short circuit. So we would like to have intake port taller than exhaust one. But if this is a geometrical solution, we cannot change this. So what we can do is introduce a charge port in which the flow can occur just in one direction. And the direction is to the cylinder. So here we have to put a charge port that is taller than the exhaust one. And so when the piston is going up, we close the intake port, but we are able to open the charge port, and we have to consider some devices that can avoid the passage of the flow of the charge from the cylinder to the charge port. So in the charge port, I should consider just the passage in this direction according to the arrow and not in the opposite one.
Why cannot we just put the intake port higher and put the device in the intake port without using the second port?
You would like to put something there to avoid the passage when...
To avoid the flow going out of the intake.
I mean, this is related to how you build the engine and to the geometrical solutions. So what we generally have here, we have some ports that can be, as being simple ports, are bidirectional. But the charge port, you have some device that maybe can be a device that can rotate. And when the piston is going down, you have not the passage through that port.
Why can't we use just one port and use that solution in the intake port to put absolutely higher than the...
I mean, here is just to call in a different way, but can be the same port in which you can cover a part of the port when the piston is going down and uncover when the piston is going up. So here is just to provide the two different names. You can have, if you want, just one port, but you have to close part of it when the piston is going down and uncover it when the piston is going up. So it can be also this solution that you are doing. Here is just to provide two different names to provide the two different functions, but can be just one single port. Okay? So here we will have just two strokes. The piston is going down and the piston is going up one time. Here you have the ports. Here, for instance, you can check the position. The piston is moving, is opening the ports. Here is called transfer port, but it's related to the intake. You can find different names, and also the number of the phases can be, as I was saying, even more complicated with respect to the four-stroke. This is the definition that we give just to have one univocal one. This is the element that I was called wedge, or is a deflector. So an element that provides that the flow is not going directly to the exit from here, for instance, directly to the exit, but you have to consider this to avoid the short circuit. Okay. We can also consider a valve timing diagram, even if we don't have valves. So this is called valve time diagram, even if we have ports. Just for uniformity, but we generally don't have valves. Yes. What we can consider is different phases that we were describing. This is blowdown that is occurring around bottom dead center. This is the intake that is occurring through that charge port or to the intake port that is open when the exhaust valve is closed. Compression and combustion that are similar to what we were describing to four-stroke engine. Expansion is also similar to four-stroke engine, also because the two strokes that we were removing were relative to the intake and exhaust, so the different phases can be similar. Compression, combustion, and expansion can be considered as similar. Here we have blowdown, opening of a port, scavenging, the two ports are both open, and here intake, so it means that only a port on the intake side is open. Here we can consider that only a port independently of the name on exhaust side is open. Here, both ports are open during scavenging process. And in fact, here you have a big color just to consider that something exhaust is going out and something fresh is going in. So two colors similar to the preceding or to the following phase. Different possibility for two-stroke engine. This was the crankcase scavenging that we were considering. Here is called mainly crankcase compression more than scavenging. And this is the most simple configuration and cheaper because we are using the bottom volume to produce the pressurization. So this is the simplest and cheapest configuration.
Sure. Is that the first is the petrol engine and in the center is the diesel engine, right?
I mean, here the engines can be either gasoline or diesel. So here they are two strokes, and two strokes can be either spark ignition or compression ignition. So this doesn't mean that this is a diesel engine. Okay. Could be a diesel engine, but this can be a general configuration. So for two strokes, we can consider either compression ignition or spark ignition because the two configurations are completely independent. The two criteria are completely independent. So here the pressurization is done by the crankcase. Here you can have a pressurization that is done by a volumetric compressor. Or you can have a turbo compressor. So we need a device to increase the pressure. Here we use the crankcase. Here we use an external device. Consider that you can have applications in which valves can be used instead of ports. So here you have intake ports and exhaust valve. So different configuration can be present on the market.
There are examples, real example of this kind of application for diesel.
Most of them can be used with this kind of application, and they can be used generally, we're going to describe, for really large engines, for instance, for ship engines. They can be used. So ship engines can be either four-stroke or maybe for bigger configuration, they can be two strokes with some advantages and disadvantages. Generally, as we are going to see, two-stroke engines can be really, really small displacement. And when I talk small displacement, I think smaller with respect to the engines that we are considering for vehicle applications. So motorbikes or applications for gardening, so lawn mowers or chain saw, so for cutting something or for cutting the grass. While at the extreme opposite, we can find really, really large engines in which the displacement can be maybe a single displacement of one cylinder of 1 cubic meter, so in which also a man can enter the cylinder. And this can be used for power production or for generally for ships. So really, really large engines in which the engine speed is really low.
So the simple engine is only can upgrade to petrol, right?
This one is mainly used for gasoline. And if this is big, no, not with this configuration that is not practically adopted, but the configuration may be with a turbocharger that is outside is mainly diesel.
So the diesel engine is
can't be used without turbocharger, right? In two strokes.
This can be used without turbocharger. This is used with a turbocharger. So it depends on how to want to obtain the pressurization. This is cheaper, but the pressurization is lower. This is more expensive, but you can have a better pressurization of the charge. You have also to pay attention to the values of the pressure, because if the pressurization is too high, you can have a higher formation of short circuit. So you have to balance the level of pressurization during intake and exhaust, because here the differential pressure is much more important with respect to the four-stroke engine. To conclude this part, maybe a couple of minutes before the break, let's try to summarize some of the difference that we can consider for a four-stroke engine. In a four-stroke engine, we are using two strokes for gas exchange process. So the gas exchange process is performed better in a four-stroke engine. And what we will get is generally higher efficiency. It depends also on the engine that we are considering. On the other side, for the two-stroke engine, we can consider that we have one power stroke every two, while for a four-stroke, there is one power stroke every four. So it means that ideally, we can expect double power for a two-stroke engine with the same displacement. Ideal. But as the gas exchange process is not as good, what we can measure is not that the power increases of 100%, but maybe the power increases of 50, 60%. So just to provide the order of magnitude. So I expect that I have a power stroke that is double the time, because in the same with the same speed I will have two power strokes with the double of the power strokes. So I can expect the power is the double, but as the exchange gas process is not that good, the power increases, but not to the what I can expect. Other comparison, in a four-stroke engine, we need valves. Commanded valves, so there is a mechanism that has to command the opening of the valves, because we have two revolutions for one cycle. two strokes. The frequency of the cycle is corresponding to the engine speed. So I can say frequency corresponds to n. So frequency of the cycle, engine speed. And so what I have is a design simplification. For instance, I can use ports. Ports that are covered and uncovered by the piston motion. Of course, ports are cheaper with respect to the design and the command of the valve. So simple and cheaper. And also, generally, what I have is a lower cost. As I have as another consequence of this, so let me one power stroke every two, or one power stroke every 4 determines that I have a better torque uniformity for a two-stroke engine. That uniformity of the torque will be related to the sum of the different cylinders. So more or less, I can consider that two-cylinder, two-stroke engine has a similar torque uniformity to a four-cylinder, four-stroke engine, because I have to sum all the torques to have the same uniformity. So similar uniformity of torque of a four-cylinder, four-stroke. Because I have to sum the contribution of all the cylinders to regularize the torque. This will be described in other chapters. We can maybe rethink about this. But anyway, start with this description of torque uniformity. What we can also say, with a two-stroke, we have lower efficiency for what was described before, but in particular, we can consider that part of the exhaust phase will be dedicated to blow down. And this, again, is connected is connected to what we were saying at the beginning of the year. Wow. Something that is related again to the number of strokes number of power strokes is that we have higher thermal loads in the case of two-stroke engine. So as the power is occurring twice, once every two revolution, in the same amount of time, I will have the double of power stroke, and so the heat given to the cylinder will be higher. And in the two-stroke, I have lower efficiency also because I have two-stroke also risk of short circuit. Fresh charge to the exhaust. And this is really minor risk when we consider a four-stroke engine. So we don't have that. I mean, we could also have part of the fresh charge to the exhaust. Short circuit can also produce what? Higher fuel consumption. If the charge is air and fuel, so if the charge is only air, maybe I have to spend to compress more air, but I won't have fuel at the exhaust. So higher fuel consumption, but I can also have, in this case, higher emissions. If the charge, maybe I can use this. Sorry, I write in here. So if charge is air and fuel, higher fuel consumption, but also higher exhaust emission, because part of the fuel that is hydrocarbon will go directly to the exhaust, and so I can have also higher emissions. So, if we consider the different engines, four-stroke engines are generally used for intermediate displacement. Two-stroke engines are generally used for really small applications. So here we are considering, for instance, maybe let me say, here can be the area of here can have, or maybe slightly for some application, I can also consider, yes, passenger car. Really small engines, I can have mopeds, lawn mowers, or chainsaw. These are some examples. Two-stroke, and they are generally spark ignitions. While in the high field of two-stroke, I can consider, for instance, power generation in large applications or ships, naval applications. And they are, as is written here, compression ignition. So we are going to describe the application of passenger cars. Here I try to provide some values. Here, this is a logarithmic scale of the power. we can consider, for instance, reference intermediate power of our application about 100 kilowatt, can be lower, can be higher. We are in the area of passenger car. Here we can have the area of light duty vehicles, the area of heavy duty vehicles, and heavy duty can be generally diesel, but we can also have some applications with maybe spark ignition engine, not gasoline, but maybe compressed natural gas. Okay, so with this one, I would like to conclude the part relative to the distinction between two-stroke and four-stroke, in which we were highlighting the phases. We provide the overview of two strokes, even if we won't discuss, because for the applications that we are considering, passenger cars, two-stroke engine are not adopted. Maybe you can find applications in the past, some trials, but these are, I mean, in the field of automotive applications, you can find exceptions to everything. We are going to describe what is the 99.9% of the applications. Okay. So we can have a 10-minute break before we start. Okay, so I've talked for a lot of time, and maybe now you can think. I can rest for a couple of minutes, and you can try to think on your own or discuss with your colleague and try to answer this question. If something is not clear, we can try to discuss together. Okay? So maybe a couple of minutes for you.
Okay. Were you able to answer? So for instance, numbers of revolution per cycle. How many? 2 and 1. So we can. Number of power stroke per cycle. Half and 1 or 1 and 1? 1 and 1. There is a power. 1 power stroke. That is the motivation for which. So 1 power stroke and 1 power phase. Power output, of course, for the same displacement, which you think is higher. 2 stroke is higher. Valves or ports. 4 stroke, what we generally have. Valves. And 2 stroke, what we generally have. Ports. We can also find some exceptions, especially for 2 strokes, but torque regularity, which has a higher torque regularity. 2 stroke has a higher torque regularity. Cooling requirements, what do you think is higher? This is a higher cooling requirement because 1 power stroke every 2. Volumetric efficiency is related to the quantity of air that we can have inside the cylinder, and so it is related to the gas exchange process, connected to gas exchange. So post stroke is higher, or we can also use an R1. Thermal efficiency that is related to, we will also call we can talk about fuel conversion efficiency. So this is the final efficiency of the engine. What you can expect. 4 stroke is better for the gas exchange process. Anyway, I can have some exception considering really, really large marine ship engines that are diesel. So, but anyway, if we consider the application for the cost, what can you expect?
Higher.
Higher for 4 stroke because you have the valves and consider all the commands of the valves. Consider that for the same application and not considering extremes or outliers. Okay. Now we can go faster considering different classification criteria because the criteria that we have described so far are the main important. So number of revolutions per cycle or working cycle, duration of the cycle, or how you ignite or how you start the combustion, self-ignition or through a spark, so forced from the external back. We can consider other classifications, so we can also have more than the ones that you are seeing here. Just an overview. Air supply means how the air is given to the engine. And we can have naturally aspirated, so the engine is directly taken from the external environment. How? The piston is moving down, is producing a decrease of pressure because the volume is increasing, and so the air is naturally moving from the external environment to the cylinder. And this is most of the engine that we can find on the market, especially in the past. Nowadays, we are including with supercharged and turbocharged. We consider an air pressurization. with supercharge, we have a mechanical or volumetric can also be, could be, even if not so frequent, also a turbocharger, but let me say generally volumetric compressor. And with turbocharge, we have a turbo compressor. Why consider an air pressurization?
Increase the amount of fuel. For the charge.
Yeah, simply because for the charge, we increase the mass of air, and therefore we can increase the mass of fuel. Why we want to increase the mass of fuel?
More power.
To get more power available. So for the same displacement, so for the same size of the engine, I can have more power. Here you can see some schematic for a supercharging. So you have a compressor that is moved directly by the engine. So you can check. So what you have that engine speed and compression speed are, so there is a mechanical connection. Here we have a compressor and a turbine. The two are connected together. So compressor speed and turbine speed are, of course, the same, but there is no mechanical connection between the engine and the element. The connection here is fluid dynamic connection. So what we are doing this. Part of the exhaust gases still have a high pressure and high temperature. So you are using them to move a turbine. The turbine will compress the air taken from the environment. So the compressor is moving, is producing a small decrease of pressure upstream of it. So the air is coming through the compressor because of the small decrease of pressure. And after it is compressed by the compressor and sent to the intake manifold. So the intake manifold is a plenum, so is an ambient big enough before the connection to the engine. So this is the intake manifold. The intake manifold can be directly faced to the engine with some ports in which the valve are installed. So we have also the definition of ports in four-stroke engine, but not, I mean, the ports is closed by the valve. And we can have also some small pipes that are called, can be called runner. They can be present or not according to the configuration of the engine. So these are the two possible configurations. Which of the two is mostly used, supercharging or turbocharging?
Turbocharging.
Turbocharge. Why?
Because the fuel power in the engine have more power.
More power. Which of the two is powerful, supercharging or turbocharging? Huh? Supercharging is generally producing a high increase of power. Actually, it's difficult to say because it's related to the configuration, but here we generally gain a higher increase of power. So why are we using turbocharging instead of supercharging?
Because turbocharging fix the engine without so much power, right?
Now, this is generally producing more power than this one.
Because of emotions.
Indra is more efficient.
Huh?
Is more efficient.
This is more efficient because here we are using part on the turbocharging, we are using part of the energy of the exhaust gases. Huh?
It is a recycle of it.
No. Here there is no recycle. We won't use this word for the moment. We use afterwards because I don't want to have confusion. So we are using the exhaust gas enthalpy to move that turbine. Let's consider it's not exactly like this, but imagine that you are wasting the exhaust gas in the external environment. So you are wasting energy because you have a high temperature. So instead of wasting in the external environment, you use to move a turbine. So it is practically, it's not exactly like that because this is producing a back pressure. So the pressure here is increasing if you have the turbine. It is like you are getting some work at no cost. It's not exactly like this, but you can have we can think really simple in this way. While here you have to use part of the energy taken from the engine. So maybe you can have a higher pressurization, so you can have more air, more fuel, more power, but you spend much more. Okay. So in particular, this can have an efficiency. So the turbocharging can have an efficiency that is higher with respect to the naturally aspirated engine. This may be as an efficiency that is lower with respect to the naturally aspirated engine, but more powerful. So more powerful, less efficient. This is, let me say, less powerful with respect to the supercharging, but of course, much more powerful with respect to the naturally aspirated. Much more efficient. Roughly, new engines, diesel engines, so compression ignition, how much is the turbocharging? Diesel modern engine, percentage of turbocharged with respect to supercharged and naturally aspirated for passenger cars. More than 99%. So almost all the diesel engines are turbocharged. Application of supercharging.
American vehicle.
For some applications, so you can say it depends on the market, but it's really small percentage. So for sure lower than 5%, for maybe lower than 1%. Let me say lower than 1-2% of spark ignition engines. For diesel engines, no applications. It's not worth it. Spark ignition engines can be either naturally aspirated or turbocharged. More or less percentage is difficult to say because it also depends on the market, but no, it can be more closer to 50, 40, 60, so 50%. In particular, this is becoming more and more adopted in recent because efficiency is higher. And so more or less the ones that are sold on the market can be Of course, turbocharged can have a higher efficiency, but is more expensive because you have more components. Injection system has to be more expensive. So it's difficult to say, but roughly we can say 50%. Mixture preparation. So how the mixture or charge is prepared. Differences between compression ignition engine and spark ignition engine. And this is a kind of historical, maybe some of them are just considered for historical reasons, are not used anymore. For gasoline, so we're talking about spark ignition engine. Carburetor was the simple system that was used up to more or less late 80s, really early 90s. Carburetor was abandoned starting from Euro regulation. So Euro 1 1992, and practically it was not possible anymore to use the carburetor because it's not fulfilling the emission regulations. Maybe we will spend a few words. So it's practically here a kind of convergent divergent nozzle is a Venturi pipe. So convergent divergent with a really, let me say, big dimension of the throat with respect to the pipe was producing a reduction of pressure. This reduction of pressure was used to take the fuel from a small pipe. So the air depression was used to move the fuel from the tank to the engine. This was placed in front of the throttle valve, and the throttle valve was used to help also the mixing of air and fuel. This, as I was saying, abandoned late 80s, early 90s. It depends also on the markets and on the configuration that we are considering. From this, we switched to injection, and we can consider port fuel injection. That is also called, we can also discuss about multi-point injection. Sorry, for the port fuel, actually we have, sorry. This is not completely true, sorry. For the port fuel injection, actually we can have, sorry. We can have single point that was used in at the beginning or multi-point. Port fuel injection is related to the fact that the fuel is injected let me think, because probably no, I would say that maybe let me I will rewrite something, because instead of considering the carburetor, we consider the injector that was able to better dose the amount of fuel. And we could have an, let me say, indirect injection that can be used is outside of the cylinder. This can be single point or multi-point. Okay, it's better if I rewrite it this way. Single point, I have just one injector for the engine. or let me say for the engine. And this injector has to place a bit upstream of all the cylinder because you have to serve all of them. Generally, it was placed upstream of the throttle valve. You could also find application in which it was afterwards, but if you place upstream of the throttle valve, you can use the throttle to better mix air and fuel. So generally, upstream of throttle valve. In multi-point, you have one injector for each cylinder. They are placed in the port. In order to be closer to the cylinder. Sorry, closer to cylinder. So in this case, we can talk about, let me say, it's better to talk about port fuel injection because in the single cylinder is not in the port, is upstream. So port fuel injection should be better used for multi-point injection system. Anyway, this is a minor distinction. So port is this part of the engine, so a small pipe between the intake line, intake manifold, and the engine itself. So this is the port in which there is the valve. So here we are closer to the engine, and with the multi-point, we have the advantage of serving one cylinder. So you can have a better distribution of the fuel, so you can inject the right amount of fuel for each cylinder. And being closer to the engine, you have a better transient behavior of the fuel injected. Other possibility is to inject the fuel directly inside the cylinder. Of course, here you have one injector per cylinder. Because it is direct. And you can have some advantages with higher cost and I mean, you have to pay more attention to the design of the engine. Most of is not always, I mean, we can consider that most of the turbocharged gasoline engine are direct injection. And most of the naturally aspirated are port injection, but you can also find the mixing. So to increase the advantages of turbocharging is generally matched with direct injection. Not only possibility, but the most frequent. So here cases are increasing, so it's impossible to give all the possibilities. So we can say that most of TC gasoline are with direct injection. So talking about frequencies, we can have naturally aspirated with port ignition, turbocharged with direct injection, not injection. Okay. So this configuration, the two last configuration are quite common even nowadays. This is less expensive and generally coupled with naturally aspiration. This is more expensive, generally coupled with turbocharged. So we can also say most here. For diesel, we can have indirect injection or direct injection. Indirect injection was not occurring in the port like for gasoline engines. But not in the port, but in a dedicated small chamber that can be called pre-chamber. So here you have the main chamber, and here you can have the pre-chamber. You can also find definition swirl chambers according to the configuration. I can generally use this pre-chamber or complete pre-combustion chamber. This was generally used up to the late 80s. Of course, of the last century. Because the injection system was not good enough to inject the fuel directly into the chamber. So there was one injector with a single hole, and there was a mechanical injector. And let me say low pressure, relatively low pressure for the fuel. Low can be order of maybe 100 bar. So the fuel was injected in a small chamber. From the small chamber, there was the passage to the main chamber. So injected here, start of combustion due to the high pressure. The piston was going down, and so through this hole, the fuel was spread to the air, so this produced a better mixing of air and fuel. Because the injection system of that time, so up to the 80s, was not good enough to spread the fuel in the whole combustion chamber, and so there was not good air-fuel uniformity. So not good uniformity of the fuel. Starting from the late 80s, it was possible to have systems that were good enough to have a proper combustion directly in the chamber. So here we have a direct injection. What we have is a multi-hole injector. Generally, we can consider between 7 and 10 holes. Really small diameter. Maybe about 1/10 of millimeter. So really small. So here we can have other problems. So for instance, clogging of the hole. So if there are impurities in the fuel, you can block it. Multi-hole injector, higher pressure. Today's is really simple to have applications with 2000 bar. You can even go higher, but just to provide an order of magnitude, higher pressure.
But whatever, yeah, the
Hmm?
upstream, injections.
The pressure here, let me say, the pressure generally is measured in a rail, so an element that connects all the injectors. So higher pressure, so high pressure in the injector rail. So upstream of the injector. And other advantage that we can have, this is no more a mechanical injector, is an electric injector. And so what we can generally have with a fast command can be, we will describe solenoidal or piezoelectric with fast command, and the advantage with multiple injections. Per cycle. So minimum nowadays, you can consider at least 2 injection pulses per cycle. So there is a small injection that is preparing the environment. So when you inject the fuel, the environment will be already ready with a high pressure related to the burning of the small amount. So at least a pilot injection with a main injection at present. This can provide some advantages in terms of combustion. And so we are reducing one of the problems that was typical of all diesel engines related also to noise. So a better behavior. Anyway, the noise is still higher with respect to spark ignition engines, but much lower with respect to old engines. Here there is another element that is this one, glow plug. That is an element that is warming up the air before the start of the engine. This will produce a better combustion for the first cycles. So generally, when you switch on the dashboard, you can see that there is something that is connected, is related to the glow plug. There is a amber light. You wait just a couple of seconds, and after you can switch on the engine. Other possible classification is related to how cooling is performed. Air cooling or liquid cooling. Now we can consider that liquid cooling is practically adopted for 100% of the vehicles. So air cooling was practically abandoned. Air cooling was used, maybe is also typical of some brands. So for instance, Porsche was using air cooling up to not much time ago. But when they decided to increase the power of the engine, particularly switching to turbocharged engines, the air cooling was not enough. And so they decided to use liquid cooling. So we can consider liquid cooling for all passenger cars, light-duty vehicles, heavy-duty vehicles that we described. In the liquid cooling, we have a system that we will describe, we will dedicate a few hours to the description of this. There is a coolant that is used to avoid that the temperature of the metal parts become too high. there is a closed system with a dedicated heat exchanger that is called radiator. There is a pump, there is a fan. Anyway, the air is used to cool down the coolant, but here we use the coolant to maintain the temperature of the metal part below a certain threshold. Consider that a cooling system is not used just to cool down the engine, but can be used also to warm up the engine, because we have to find a right balance for the temperature. So we want that the temperature of the engine is high enough, but not too much. At the beginning, the cooling system was used just to prevent the high temperature. But since a few years, cooling system is also used to warm up the engine in a fast time, because high temperature for the engine means reduction of friction and so increase of the power that we can deliver. But few lectures will be dedicated to this, all the parts, all the detail. Instead, for air cooling, that can be still used for small engines. So for instance, two-stroke small engines can be considered with air cooling. You have some external finnings on the air that are used. For instance, if you have a moped, the external air can be used to cool down the moped through this, the presence of these finnings. In which you have to dimension the thickness, the distance, and so on. But for passenger cars, this is practically not used. Okay. Other possible classifications are related to the shape of the engine and how you arrange the cranks. Motivations of crank arrangements will be related to dedicated chapters to balance. So you can have inline configuration in which all the axes of the cylinder are on the same plane, vertical or always vertical. For big engines, generally you consider that the cylinders are in generally two planes, and this is because you want to short the length of the engine, otherwise it becomes long. So for instance, this can be adopted when the number of cylinders is 6, 8, or even more. Opposite cylinder, here I have boxer. Sometimes someone is distinguishing between boxer and opposite cylinder, but anyway, we will enter the detail afterwards. This can be seen as a V, in which the angle of the V this is the V angle. Here, the angle is equal to 180, so you open. This can be considered anyway alternative not to a V engine, but sometimes is alternative to an inline. So you can find, for instance, 4 inline cylinder or 4 boxer engine. This is mainly related to the manufacturer. So for instance, Subaru is using this kind of application, is quite widespread. Other manufacturers were using this in the past. So for instance, Alfa Romeo was using in the past, nowadays mainly related to inline. We can see, we can provide some hints, possible two advantages, but it's mainly related to the know-how and to how you would like to use the space in the bonnet. So this can be taller, but not so wide. This in the bonnet, in the compartment, is wider and is not so tall. So it's related also to the space utilization. Not much difference from the torque uniformity, for instance. Some difference in the balances. We can try to provide some hints.
Teacher,
But anyway,
what about the Das Auto's W engine?
W engine is a V engine. Instead of having two bands, you have three bands, for instance. But W engine, you're talking about W engine. W engine can be used, for instance, if you have 12-cylinder engine, but it's not so widespread. I mean, you can find some application. It's an exception, what you say.
So what is the angle?
The angle is related also to the number of the cylinder and to the configuration that you can consider. Sometimes you are forced to use a certain angle according to the disposition of the cranks, the length that you want to consider, but we will provide some details afterwards. So this was an overview, it's the first chapter, so I cannot answer all the questions now because otherwise we will finish the course with just one chapter. So, but we will have time maybe to discuss something, at least to check some details. Right? These are configurations that maybe can be used, some exceptions. This was used a lot in which kind of application? Now it's not used anymore. Airplanes, when the airplanes were endowed with internal combustion engines. We have a small museum at the Polytechnical with this kind of engines. Airplanes, let me say, until in the mid of the Second World War, so in the 40s. When the engines were, when internal combustion engines were used for airplanes. Starting from Second World War and after the Second World War, no internal combustion engines are used for large engines, can be still used for really small engines for tourism or for entertainment, let me say, really small engines with two places. Bigger engines with kind of engines of day, large engines, large planes, which kind of engines? Gas turbines. Okay, so here I have reported some YouTube videos relative to four-stroke, two-stroke. Here curiosities about Wankel and Stirling engine. Questions from your side? Maybe I dedicated a bit more time on the first chapter just to maybe sometimes answering some curiosities, or maybe to start not too fast. We can conclude here the lecture. Next week, on on Tuesday, we will start the second chapter. The Monday is used for the labs, but we won't start the next one. Probably we will start the following one. I still have to discuss with my colleagues, so we will give you also time to divide you in groups. Next week, we will have lectures on Tuesday and Friday, and the applied lecture on Thursday. Okay? I will write also on the website of the course. Have a nice weekend. See you on Tuesday.
Actually,